Hi guys, welcome to the lecture on carbon chemistry. Um, now, we've spent a little bit of time in our introductory chemistry really doing what's called inorganic chemistry. And the next step in the sequence is to talk about carbon chemistry, which more aptly should be called organic chemistry. Organic because um, it has to do with organisms. Organic because it has carbon. And, and, um, and I'll fill you in on some cool details. Hopefully, you recognize this broadcast here. This is obviously NBC 10, and that's the Philadelphia broadcast. And you might recognize this image. It's pretty powerful. And it was taken down in Southwest Philadelphia at the Sunoco refinery just a few years ago. And off to the left hand side here, you can see a cracker unit that is blown out of there. And I think that was like 30 tons or something. Maybe it was 300 tons or something crazy, but I think it flew a quarter of a mile. And of course, what they're doing down there in the refinery is refining crude oil, which is organic compounds. We know that crude oil comes from fossils. You know, crude oil is a fossil fuel, and the the oil reserves we get actually come from deposits of marine organisms. Okay, so oil is an example of marine fossils, and they've been buried for a long period of time, and they're compressed and turned into this black tarry stuff. You can bury forests too. That makes coal, which is the other fossil fuel, which is a really dirty fuel. We should not burn coal, but we do here in southeastern Pennsylvania. It's one of the worst places in the country. And coal-fired power plants are one of the worst contributors of CO2 to our environment. So if you're an environmentally conscious person, which I hope you are by the time you leave my course, um, you'll take actions as adults to try to limit fossil fuel usage, coal particularly here in southeastern Pennsylvania and in our country and around the globe. Anyway, yeah, hydrocarbons burn real good, and that's because of all the energy stored in the chemical bonds. So, carbon chemistry is organic chemistry, and if you are a chemistry student or you're a pre-med student or nursing student, organic chemistry is one of those courses that will give you night sweats, night terrors, and of course it's all about biochemistry. What is the chemistry of life? And the chemistry of life is carbon chemistry. It is organic chemistry, but and you can see here I'm zooming in on an electron micrograph of some flea, and on the flea's eye is some other bug, some other bacterium. So what are we really made of? It's a shame you can't. Well, you can. They have very sophisticated microscopes today that allow you to image an atom. You can't really see an atom, but you can feel it out. And so this micrograph gives you a little insight into what we're going to try to do. We're going to try to understand how these things work at a basic level. And so we'll learn about those major classes of biological molecules: carbohydrates, lipids or fats, proteins, and then finally nucleic acids. But before we begin, let's talk about carbon. Now, remember that when I taught you about the orbital shells, I said that I'm going to tell you some useful lies. And one was that there was a 1s shell and then a 2sp shell. Well, that's a bit of a lie. Truth is that, in fact, in the case of carbon's bonds, the s and p orbital shells, combine to form something called sp hybrids. And that makes carbon unique. And that makes it really good at forming big molecules. In fact, it's the basis for polymer chemistry. Carbon chemistry is polymer chemistry, and polymers are like chains of beads. Okay? So carbon can form 4 bonds. It forms a tetrahedral configuration, and we denote it this way. We have 2 solid lines to represent um, bonds that are in the plane of this board that you're looking at, and then one bond that points out at you, and one bond that fades into the background here. So you can sort of see it better in this 3D illustration, right? So these two bonds are in the orbit of are in the plane of the piece of paper that they're drawn on, but this bond is kind of shooting in the back. This bond is kind of coming out forward. So that's what that means. Of course, you can represent this molecule this way as well, and it's methane. It's CH4. It's the simplest of the carbon compounds, right? I've talked to you guys about making simple molecules, right? If you talk about a simple carbon compound, well, the most common element for it to combine with would be hydrogen. So when I combine one carbon with 4 hydrogens, I get the molecule called methane, or CH4. 2 carbons with 6 hydrogens gives you ethane. 3 carbons with 8 gives you propane, butane, and this form of hydrocarbon are the simplest hydrocarbons, and they're called alkanes. Okay. The alkanes all have this same generic formula, C to the N, H to the 2N plus 2. So if there's one carbon here, then it's H2 times 1 plus 2, 4, C4, CH4, methane. If it's C2, then it's H2 times 2 is 4 plus 2 is 6. C2 is going to give you H6, ethane. And on down the line, right? So butane C4, H2 times 4 is 8 plus 2, C4H10. And these are the alkanes. They're simple hydrocarbons. They're alkanes because every single bond is a single bond. All right, so I've just got carbon-carbon single bonds. And, as I extend those chains out, one of the things that can happen is I can have isomeric forms of that. So here's our buddy octane. And I can draw it out this way, which is complicated and hard, or I can draw it this way, where each point on the line represents what's called a fully saturated hydrocarbon. That is a carbon that has as many H's as it can carry. All right, so this is 1, 2, 3, 4, 5, 6, 7, 8. That's the alkane called octane for 8. But octane could have multiple configurations, multiple isomers. In fact, here's a whole list of the isomers there. I could take this group here and stick it there, add it on there. And then, or I could stick a couple groups here. In fact, the best isomer of octane is right here. 2,3,4 trimethylpentane, which is still octane, but you can see I've got it all bunched up, and that stuff burns really good, and that's what you find in your car. Well, the fact that carbon makes so many bonds so readily underlies the fact that it's the building block of life, okay? In carbon chemistry, organic chemistry, in essence becomes polymer chemistry. So when you think of carbon and oil, I want you to think of plastics, because they're all polymers, okay? And in every case, a polymer is kind of like a chain of beads, all right? Proteins are polymers. Carbohydrates can be polymers. Fats are polymers. Nucleic acids are all polymers. So when we talk about biochemistry, we're talking about polymer chemistry as well. And in a polymer, I take little beads and I join them together. Sometimes the beads are identical, sometimes the beads are different. But they very often come together in a process called dehydration synthesis. And so I've got an illustration here. This is an amino acid, and you can see it's got an oxygen group here. Here's another amino acid there. They come together and they lose an OH. They lose an OH. And that's why we call it dehydration synthesis. We lose water to join these monomers together. All right, so we take monomers together to make polymers, and that, in essence, is biochem. And so in biochemistry, we take these monomeric units and we create polymers, and we call those large molecules biological macromolecules or biomolecules. And so that's the topic for our next video. And hope you enjoy that. See you on the other side.